Okay, so today what I would like to go over are ions, electron configurations for ions. Before we start going over this, I want to review some terms that we went over the other day because these terms will be important as we do ion configurations. The first term is isoelectronic. Now, sometimes when we form ions, what you will see is that the configuration for the ion will have the same configuration as a neutral atom. So that's an isoelectronic configuration. Another term you will see is that when we're looking at configurations, some electrons in that configurations will be the core electrons. Those are the ones in the lower energy levels. Typically, these will not be disturbed when we form ions. The valence electrons, those electrons in the outermost energy level, will be the most important electrons, and those will be either lost or we will add electrons to those valence electrons. So if we look at the next slide, what I want you to see here is that both of these elements, silicon and germanium, have 4 electrons. If you look at silicon's electron configuration, those 4 valence electrons are in the third energy level. Those are the 3s2 and 3p2 electrons. Germanium, which also has 4 valence electrons, its valence electrons are in the 4th energy level. That's the outermost energy level. Those are the 4s2, 4p2. What I want you to notice here is the 3d electrons are not part of the valence electrons. Those are actually considered to be core electrons. So as you see, these both have 4 valence electrons. So when we form ions, remember, electrons are lost or gained when we form ions. Negative ions have gained electrons. Positive ions have lost electrons. And remember these terms also. So I'm going to ink these here. The anions are negative and cations are positive. So we're going to be adding electrons or removing electrons from the highest energy level number, and that is we are adding or removing valence electrons. So let's go to the next slide. What I have here is 10. I have highlighted the valence electrons, and what I want you to notice is when we form the ion, the plus form ion, we're taking away those valence electrons to form just krypton 4d10. When we form the plus 2 ion, we are taking away electrons from the 5p because that's a slightly higher energy than the 5s. So I'm actually going to write that in here. 5p has more energy than 5s. Okay, so we're always taking away electrons from the highest electron energy level, not the highest energy orbital. Okay, if we look at the next slide, here we have a negative ion. We have bromine -1. Notice here the bromine, neutral bromine atom has a partially filled 4p sublevel. When we add 1 electron, we add it to the highest energy level and highest energy sublevel, which is the 4p, and that becomes filled. What I want you to notice is that is isoelectronic to krypton. So this is isoelectronic with krypton. So we will often see this when we form ions, they will become isoelectronic with a noble gas. Okay, so let's look at the worksheet that you guys have on Google Classroom, which is going to be your homework. So on this worksheet, When it asks you for electron configurations, you can either do longhand or shorthand. It's your choice. So I'm going to do a few problems on this sheet. I first want to do cesium. So cesium, we have, let's see, it's in the fifth energy level, the sixth energy level number. So its noble gas is xenon. First, we're going to write the neutral atom. So it's going to be xenon and 6s1. So when we form that +1 ion, it's going to become isoelectronic with xenon. So this is cesium +1, and this is cesium. So it becomes isoelectronic with a noble gas. Now, when we write the orbital notation, you may be tempted to just write down brackets xenon, but there is no such thing as a shorthand configuration in orbital notation. So we're going to have to just write that out. It's going to be 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. And that is our configuration for cesium +1. And will notice that that would be the same configuration as xenon, but like I said, there's no shorthand orbital notation. So now let's do a negative ion. So let's look at oxygen -1, -2. So here, if we were at the shorthand configuration, that would be helium, and that would be 2s2, 2p4. We add 2 electrons to that partially filled p sublevel. You will never have a situation where you have an anion where you have to create a whole new energy level, so you should never see that. So this is going to become helium, not xenon, 2s2, 2p6. And what you should notice is that is isoelectronic with neon. So you could also write neon. And the the orbital notation for that one would be 1s, 2s, 2p, and that's it. Okay, so now I want to go down and do transition metals. So let's look at silver +1. So again, when you're doing these, always write out your neutral atom first. So we have silver +1, that's in the 5th energy level. So the nearest noble gas would be krypton. That would be 5s2, 4d9. Remember, this is one of the exceptions, so we have to adjust that. That's going to be 5s1, 4d10. This is silver. Now we have silver +1. That's going to be krypton, 4d10. Now this is not isoelectronic with a noble gas. However, it's a very stable configuration, and we have a +1 ion. We wrote the orbital notation for this one. We would have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and then 5s, excuse me, not 5s, we would skip that, and then we would have 4d. Okay, so try all the other problems on the sheet. And then if you have any questions, please feel free to email me.